Hello class, in today's video we're going to be looking at isomers and drawing hydrocarbons. The learning intentions of today's video is we're going to develop an understanding of what isomers are, and we're going to learn how to draw isomers of very simple hydrocarbons. So before I start off today's lesson, I do want to kind of revisit over some of the questions that you did for me towards the end of last lesson. So towards the end of last lesson, you were naming hydrocarbons. Specifically, you were naming alkanes. But something that I'm not too sure whether you picked up on was that I've actually got you to draw or name, hydrocarbons that belong in the same family. So for instance, you were drawing two molecules of pentane, but they only differed in the position of the double bond. And similarly, you've also named two hexane molecules, but they only differed in the position of the double bond as well. Now, the following pairs, as you can see, have they have the same identical chemical formula. So if I was to write down or count the individual atoms, both of these are going to be the same. However, as you can see by their structure, they do look very different. What we're going to be looking at in today's lesson is we're going to be looking at mainly compounds that do have the same exact chemical formula, but they have different structural formula. And what does this actually mean in terms of how they behave and the chemical properties and whatnot? Now, I've also got another examples over here. So these two hydrocarbons are both alkanes. As you can see, they're alkanes because they have single to single carbon bonds. And they also have the exact same chemical formula, but as you can see, they are rearranged or connected very differently. So they have a different structural formula. Now, just as an estimation or what your prediction is, but what do you think, what would their names be? Do you think they would have the same chemical name and the same chemical properties, or do you expect them to have very different chemical names and different chemical properties? So comment on your answers on the right hand side, and then we'll continue with today's lesson. Alright guys, so the short answer of this is they're going to be no. So they will have very different names and different chemical properties. And the reason why it is because they are connected in different ways, or the rearrangement of atoms is different, they are going to have slightly different chemical properties and also undergo different chemical reactions as well. And since they do behave very differently from each other and they do undergo different chemical reactions, we do need to actually give it different names so that we can actually differentiate between the two compounds that do have the exact same chemical formula. Now, what I'm going to show you right now is something kind of beyond the scope of what we need to know, but might be very interesting to you guys. And this is something usually learnt in VCE, so Year 12 specifically, but in more detail in university. So this is a case study over here. So between 1950 to 1960, a drug which is named as thalidomide was developed in Germany, I believe, to help treat morning sickness in pregnant women. Okay, so this is the chemical structure of this particular drug, and they and doctors and pharmacists, or whatever you call it, they used to give out this particular medicine to women who were experiencing morning sickness, so like where they vomit in the morning generally. And initially it was deemed to be safe and it was deemed to be effective. So it was actually curing what it was supposed to be actually targeting. However, they found that this also caused birth defects in some, and the key word over here is in some pregnant women, okay? And I do want to kind of state that this is not a side effect at all, because a side effect is usually where the drug usually cures the main thing it's supposed to do, but then it also causes other unnecessary or like secondary effects as well. But this isn't a side effect because the drug didn't cure morning sickness for those pregnant women that did have those birth defects. So as a result of this, the drug was quickly removed from the market, and scientists were conducting a lot of research to find out why was this the case. And what they actually found was that that there were actually subtle variations in the drugs given to the patients. So what I have over here is I've got two images of the drug. Now you might think they look the same, but if you look closely, there is a difference between this. And this is, as I'm saying, this is kind of beyond scope. But what this is saying over here is that this portion over here is like, think of it as it's behind and this is in front, whereas this is in front and this is behind. Now you're probably thinking, does that make a difference? Well, it turns out it does actually make differences, because even though they look the same, I want you to think of this as being your left hand and your right hand. So this is an analogy of here. Although your hand is still a hand and they're kind of the same, the orientation, I guess, is slightly different. As a result of this, they still behave very differently. So chemists learned that drugs with the same chemical formula as well as the same chemical structure can still have different chemical properties as well as pharmaceutical effects. So this was a major discovery, and what they learned was something referred to as enantiomers. And you don't need to know this because this is going to go over your head. And even Years 12 students didn't struggle with this because this was initially a topic learnt in university. But I do want to show you something quite interesting, that drugs can have different effects although they look the same and although they have the same composition as well. But anyhow, we're going to be looking at something referred to as isomers today. So isomers are compounds that have the exact same chemical formula, meaning they have the same composition, they're made up of the same atoms with the same number of atoms, but they differ in terms of their structural formula, so in terms of how they're connected and rearranged. Now, if both of these compounds have the exact same chemical formula, but the number of carbons in the main chain are different, both structures are considered to be isomers of each other. Now, what do I mean by the number of carbons in the main chain? We talked about this in the last lesson, but notice that in this example over here, you've got 4 carbons in the main chain. So if you can draw a circle around all the carbons without like lifting up your pencil, that's kind of the main chain right there. Whereas in the second example over here, the longest chain that I could do without lifting up my pencil is 3. So it contains 3 carbons. There's no way for me to include this carbon without kind of overlapping or lifting up my pen in this case. So as a result, they're going to have different names compared to each other. Another thing that I do want to point out is that compounds that are mirror images of one another are not considered to be isomers at all. So in this case over here, you've got 2 compounds that may appear to be isomers because the position of the chlorine is different. However, these are pretty much the exact same compound, because if I was to flip this over or did a mirror image, they're going to be exactly the same way. Similarly, if you were to look at this from the other direction or from a different point of view, you would see that both of these are going to be the same. But I'll also show you why this is the same in terms of how we actually name it, and this is going to go slightly beyond what you need to know, but this will prepare you for year 11 and year 12 VCE. So in this case, if we were to name this, we haven't named things that contain other substituents, but if I also name this, the same steps applies where I identify the main chain in this case. And once I've identified the main chain, I just need to number it from left to right. Okay, so I can name it 1, 2, 3, 1, 2, 3. Similarly, I can name this 1, 2, 3. 1, 2, 3. After we've named this, we need to ensure that the carbon that contains either the double bond, but in this case, or another substituent has the lowest number assigned carbon. So in this case over here, if we're looking at the molecule towards the left, you would agree with me that chlorine is going to be found on carbon 1 when the carbons are numbered from left to right. So this one would be called 1-chloropropane, propane because it contains 3 carbons, and chloro because it contains the chlorine substituent. That's how we name things. Similarly, if you look on the right hand side over here, if we were to number it from left to right and have chlorine on the lowest assigned carbon, this would be again 1-chloropropane when you number it from right to left. And in this case over here, it's quite apparent that these are not isomers and they have the exact same name. So what I'm going to do now is I'm going to show you some questions, and I want to get you to see whether you can identify whether the following pairs of hydrocarbons are considered to be isomers, or are they identical compounds, or are they different compounds in general. So for the very first one, are the following molecules considered to be isomers or not? Now, I'm hoping for this particular question over here, you've answered yes. And the reason why that is because that they both have the exact same chemical formula. However, they have different chemical structure. In this case over here, although it appears zigzag, we refer to this one as a straight chain or a linear one. Whereas this one over here, if I was to draw the main chain for containing all the longest carbon atoms, this is what it would look like. And as you can see, this only has 1, 2, 3, 4, 5. five carbons in its main chain, whereas this has 1, 2, 3, 4, 5, 6, 7 carbons in its main chain. Everything is still the same. The composition is still the same. It's just different structures. As a result, they're considered to be isomers. For the next example, have a go with this one as well. And for this one, I'm hoping that you've also answered yes. So these pairs of molecules are considered to be isomers of one another. In this case over here, they're isomers because the position of where the double bond sits is different from both of these molecules. So this sits in the first carbon over here, whereas this sits on the second carbon when you name it from right to left. Have a go with this one as well. So do you think these pairs of molecules are considered to be isomers? I'm hoping for this one you also answered yes as well. So in this case over here, if you were to identify the main chain, notice that in this example over here, this has 4 carbons, whereas if you were to draw the main chain for the other one, this is what it would look like. So this has 3 carbons, 4 carbons, same chemical formula, therefore they're considered to be not isomers of each other. Have a go with this one. This one's slightly more tricky. And if you answer this successfully, you would realize that this is not considered to be isomers of each other. Now, the reason why they're not considered to be isomers is because if you were to actually count the number of atoms and write down the chemical formula, this over here has 1, 2, 3, 4, 5 carbon atoms, and it has 3, 5, 7, 10 hydrogen atoms with 1 oxygen atom, whereas the other molecule on the right hand side, this contains 1, 2, 3, 4, 5 carbon atoms, 3, 4, 5, 7, 9, 12, and 1 oxygen atom. And as a result, because they have different number of hydrogen atoms, they're not considered to be the exact same, or they're not considered to be isomers of one another at all. So that's why I've answered as a no. Have a go with this one over here. So if you answered this one successfully, then you've also would have found out that this one is going to not be isomers of one another. The reason why they're not considered to be isomers of one another is because that this over here, this molecule contains more hydrogen atoms than this, and in order for it to be an isomer, it needs to have the exact same composition, the exact same chemical formula. That's why these are not considered to be isomers of each other. Very last one. So in this case over here, identify whether the following molecules are considered to be isomers of each other. If you answer this correctly, the answer of this is going to be no. And the reason why this is no is because that although they have the exact same chemical formula, these pairs of molecules are considered to be identical. They're the exact same chemical or the exact same compound, because all I've done in terms of drawing the structural formula is that I've just moved this CH3 group as an L shape, but I could have done this CH3 like this and put the hydrogen over here as this. And if I did that, then these two would appear the exact same. So in this case over here, they're considered to be identical compounds. What I'd like you to do right now in the next 20-30 minutes or so, because the worksheet is quite long, I want you to spend your time answering these questions. I don't really need you to answer all the questions. These questions I will have put on as a separate PDF file. These aren't all the questions that I'm showing over here. So please spend 20 minutes or so answering those questions inside your exercise book, and then we'll go on to the next topic. So what we're going to be looking at now for the remainder of today's lesson is how do we actually draw isomers. And there really isn't an easy way of drawing isomers at all, because it's going to involve some level of trial and error. So I've got the 3 steps over here that you need to follow. First of all, if you were given the chemical formula or something, what you need to do first is draw the straight chain version. So to help you understand what I mean by straight chain, I've got an image over here. So straight chain is where you have all the carbons going from left to right or up and down pretty much, okay? So there's no branches, whereas this one over here contains branches, okay? What you need to do next is you need to trial and error by drawing another compound with a branch that's not found at the end of the hydrocarbon. And afterwards, you need to ensure that you refer back to your drawings to ensure that you're not doubling up, because you might be drawing images or mirror images of another compound, and we said earlier on that compounds that are mirror images of one another are not considered to be isomers. So in the first example over here, you need to draw isomers of pentane. So how many isomers does pentane have? Now we know that pent, remember, it means 5. So this one has 5 carbon atoms. And because it has an suffix, this is an alkane. And we know that all alkanes follow this particular formula over here. So if you were to substitute 5 into this formula, it would be C5H12 in this case. So you need to draw all the variations of a hydrocarbon that has this same composition, the same chemical formula, but a different structure, okay? So the connectivity is a bit different. Now, if you were to draw this successfully, what you need to do first is you need to draw the straight chain version. So I want to draw the straight chain version like this. Okay, so this is one variation of pentane. It could appear to be a straight molecule. Now, what I need to do next is I need to, process of trial and error, I need to include some branches in my molecule so that I can draw another isomer. And I need to include the branches that's not found on the ends. So meaning that do not put a branch on the ends of each of these carbon atom. So in this case over here, what I could do is I could do something similar to this. I could do this. So in this case over here, I've got 4 carbons in my main chain, but what I might do is I might add in the last carbon atom like so. So if I was to do this, this is what it would look like. So hydrogen here, hydrogen here, hydrogen over here, okay? So that's another isomer of pentane. Now let's see if we can draw another version of pentane, and if I also do this, it would look something similar to this over here. I could draw my pentane like this. Now, although I'm saying I'm drawing another version of pentane, technically they're not considered to be pentanes at all because they have a different structure. The naming is a bit different, so please ignore what I meant by that, but I think you know what I mean in general. So in this case, although it appears messy, this is another version because as you can see, this has 3 carbons in its main chain. This is an isomer because it contains 4 carbons in the main chain. This is different because it has 5 carbons in the main chain. As a result, pentane only has 3. Now, some of you guys probably can't read my ugly handwriting over here, so this is a neater version of what I've pretty much illustrated. Now in this case, as you can see, they have different structures, and because they have different structures, they have a different name. In this case over here, you might have drawn other versions. So in this case, you might have drawn something like this over here, let's just say. And if you draw something similar to this, I can confirm that this is not considered to be a unique isomer because these are pretty much mirror images of one another. So that's what I mean by please make sure that you refer back to your actual drawing to see that you're not doubling up by drawing mirror images of one another. Please make sure that when you're doing this that you are following the octet rule. So remember that hydrogen can only bond to one single atom. Some of the common mistakes that I see is something similar to this. I might say carbon. I'm just going to draw dots over here because they might continue something else. But in this case of here, this is not plausible because hydrogen only has 1 electron to share. There's no way that hydrogen can bond to 2 separate atoms. Hydrogen can only bond to 1 single atom. So please make sure you are not making this mistake over here. Alright guys, I want you to have a trial and error. This will take you a long time because you might be doubling up. So spend 10 minutes or even 15 minutes to see whether you can draw unique isomers of hexane. So hexane, remember, is C6H14. Try to draw all the alternatives to have the exact same chemical formula but different structure. So have a go, pause this video right now and see how you go. If you've done this correctly, then you would find out that there's actually in total 5 isomers of hexane, and this is what it would look like over here. So I'm just going to leave this over here for a bit, and please pause this video to see whether you've drawn this correctly or not. If you have, great job, because this is a common topic that most students, even in year 12, get wrong as well. So what I'd like you to do for the remainder of today's lesson is I just want you to answer these 3 questions. So it's not going to take you too long at all. So this is the end of today's video. Hopefully this video helps you. I'll see you guys again in the next video. Bye.